All right, we're back here with part B of our free fall topic, and I'm just wanting to get my pen up here. Again, I should have done this before. All right, and we're looking at a couple of problems. So if you remember, we were discussing free fall in our last video. And free fall is when we take objects and we let them undergo constant acceleration. That constant acceleration is what we refer to as gravity, and that value is always going to be 9.8. So anytime we have something falling, we're going to start to know that that's constant acceleration, and it's going to have an acceleration of 9.8 meters per second squared. All right, so we can see that we've got our first problem here. It's we got a construction worker. He accidentally drops a brick from a high scaffolding. And what's the velocity of the brick after 4 seconds, and how far does the brick fall during this time? So I like to draw pictures. Again, maybe it's just the artistic point in me. Here's my construction worker. He's up on the top, and oops, there's that brick, okay? And that brick is going to start to fall this direction. So what we're going to do is we'll define this as being my positive direction. So I like to do down as a positive direction sometimes because that's the only motion, and I like my motion to always be mostly in the positive direction. So again, it says drop from a high scaffolding, so I'm going to make this a little bit higher. And we know that it takes time is equal to 4 seconds for it to fall. So how far, is the question, does the brick fall during this time? Now again, I like to draw my picture, and I like to list out those 5 different variables that I can kind of see. So I got a VI, I got a VF, I got an A, I got a T, and I got a D. So those are the variables that we looked at last time when we had our constant acceleration problems. The only difference here is because we dropped something, the A is 9.8 meters per second squared, okay? And the time was given to me as 4 seconds. The distance is what I'm looking for, so how far does it fall? And we also want to know the velocity at the end, and we know that it was dropped at the top here, so it had 0 meters per second starting with. So essentially I'm putting question marks or putting numbers by everything, and now I'm going to try to solve for this. The first route I want to go is I think I'm going to go for this information first, because I have an equation, VF equals VI plus AT. That is my second relationship, so I'm going to call that, again, that's my one I call equation number 3 of our 3. And I'm going to plug in some values here. So that one is my unknown. This is 0 meters per second. This is 9.8 meters per second squared. And then this is 4 seconds. So I'm just going to take my 9.8 times my 4. And I end up getting 39.2 meters per second. That's my velocity. Okay? Straightforward type of a problem. All we have to do is, again, pick out that information and find that. Now we know that one. Okay? It gives us some routes of how we can go about doing the second part. Now, my one tip is generally to do this. If I can do this problem without using that number, that's the best way to do it. So I'm going to go back here, and I'm going to say, let's take this piece, this piece, this piece, and this piece, and see if we can find an equation that we can do this with. Okay? So I look up on my board here, and I see that I have that first equation, which has D equals VI T plus 1/2 AT squared. So in other words, I don't have to use that answer, which means that my chances are better if I got that one wrong, that I'm not going to get this wrong as well. So I'm going to set it up using that. The D is what I'm looking for. VI is 0, okay, meters per second times 4 seconds, plus 1/2, 9.8 meters per second squared times 4 seconds quantity squared. So now 0 times 4 is just 0, so that piece disappears on me, and I like any time that I start from rest or that I have initial velocity 0. It makes life easy. So now my distance is just going to be 1/2 9.8 1/2 of 9.8 times 16. So I'm just going to go 9.8 divided by 2 times 16, and I get 78.4 meters. Okay, so there's my two answers for that problem. Okay, now keep in mind, did we know how much mass the brick had? No. Okay, mass is not important when we start dropping things. It's all about objects fall at the same rate, so just keep that in mind. Now, we do have some things when we get to topic set 4 that we'll talk about, and we'll fix those. But ultimately, you know, on Earth, everything falls exact same rate. Next problem, okay? Now we got a tennis ball is thrown straight up, and I don't know if I have any tennis players in this class, but you know, every now and then we have to throw various balls up into the air, and so this time we chose a tennis ball. All right, so a tennis ball is thrown straight up with an initial speed of 22.5 meters per second. It's caught at the same distance above the ground. How high does the ball rise, and how long does the ball remain in the air? So here we go. I'm going to draw my little picture. So here's my tennis player. Okay, and here's the tennis ball, and we're going to throw it up into the air, and then they catch the ball right back here at this height. Okay, so in other words, we have ball goes up, hits a point up here, and then ball comes back down. Okay, now if I think about this, the ball starts with that velocity and it's slowing down, slowing down, slowing down, slowing down. This becomes very important. Okay, this point right here at the peak is kind of an important point to me. It's that point that says my velocity all of a sudden stops. Okay, I have a velocity that's equal to 0 meters per second. And I like to have those things where I have those points where I have 0 meters per second. Now, I have two situations that I can deal with here. I can treat this problem as if I was standing up on a piece of scaffolding and I was dropping the ball, or I can say I'm going to throw the ball and it's going to come to rest at some point in time. Okay? Because I already did the scaffolding problem, I'm not going to treat it like I'm dropping it. I'm going to treat it like I'm throwing the ball up. So in other words, I'm going to define this as the positive direction. Positive direction is going to be up. So now I'm going to list out my VI, VF, ATD, and I'm going to start plugging in some numbers. So now down here is where I have my initial velocity. My initial velocity was 22.5 meters per second. My final velocity, I'm going to take the final velocity at the peak here, which is going to be 0 meters per second. And now my acceleration acts against my positive direction, so that's a negative 9.8 meters per second squared. And what we don't know is how long does the ball remain in the air, or how long does it take to get to that peak, and we don't know how high it got. Okay, so I'm going to do this problem using this information. I'm going to use this piece, this piece, this piece. I'm going to solve the distance part first, because that's the first question I have. How high does the ball rise? I'm going to set this thing up using now an acceleration and two velocities. So I'm using equation number 3. So it's VF squared equals VI squared plus 2AD. Okay, and I'm going to solve for my D. That's the one I'm going to solve for. My VF is 0, so 0 squared is still 0. VI is 22.5, so I'm going to do 22.5, and I'm going to square that. That comes out to be 506.25. Now that's actually, if I think about it, it's meters squared per second squared, okay, because we squared that value, plus 2 times, now this is a negative 9.8 meters per second squared times d. Okay, so I'm going to bring this value to the other side, so I get negative 506.25 equals 2 times 9.8 is negative 19.6d, and I'm going to divide by a negative 19.6, negative 19.6, so now d comes out to be 506.25 divided by 19.6, 25.8 meters, okay? Because now again, remember this was meters squared per second squared, and this was now meters per second squared, meters per second squared. The second squareds cancel, one of my meters cancel, and so that's how I left myself with just meters. And that's how high it got before it started to turn around and come back down. Okay? So that's my answer to the first part. Now, second part was, how long does the ball remain in the air? So in other words, how do we solve this time component? And I'm going to go with that equation, again, not using the D. I'm going to use the VF equals VI plus AT equation. My VF is going to be 0. My VI is going to be 22.5. My A is a negative 9.8. And my T is what I'm solving for. So I bring my 22 over to the other side, so negative 22.5 is equal to negative 9.8 T, divide by negative 9.8, and T now is equal to 2.3 seconds. Okay? Now, that time represents the time it took for the ball to get to the peak, not the time that it took for the ball to get to the peak and back down. This is why when I first was talking about this problem, I said I could treat this like I was dropping it off the scaffolding. This has symmetry. So in other words, the time it takes to get to the peak is going to be equal to the time it takes to get back down, and the ball is going to have the same velocity here as it had here. And so we can use that fact to kind of get my, what we call hang time. Okay? And my hang time is essentially twice whatever that time was to get to the peak. So I'm going to take this number right here, and I'm just going to double it. And that gives me 4.6 seconds. And that's the amount of time that the ball stays in the air. Okay, remains in the air. All right, so now hopefully you kind of understood those two questions. We'll have a couple of questions that deal with free fall, but we should have a pretty good understanding at this point in time, again, dealing with these problems. This is the last video for this topic set, so we are now looking at taking a test here, probably within the day or so. So, all right, until next video, which won't be until topic set 3, well, have a good night.